Hello students, today we are going to discuss about single sideband suppressed carrier. This comes under first unit and course outcome 1. Distinguish between amplitude modulation communication systems. So in the previous class we have discussed about double sideband suppressed carrier and double sideband with full carrier AM modulated waveform. Today we will discuss about single sideband suppressed carrier. So in AM with carrier, both the transmitting power and bandwidth is wasted. Hence we preferred a DSP-SC. But even though we suppress the carrier component, we can achieve only 66.67% in DSP-SC. To improvise the efficiency level, again we are going to suppress one of the sideband along with the carrier. That is why it is called a single sideband suppressed carrier AM. So this block diagram shows the SSB AM. That is, the modulating signal is given to AM modulator. It is a balanced modulator. One of the input signal is directly given to AM modulator, whereas the second one is 90-degree phase shifted. Then the phase shifted waveform is given as the input for AM modulator. Similarly, carrier signal directly given to one of the AM modulators, and 90-degree phase shifted is applied to another modulator. So here we have one summary. By adding these two phase shifted modulated waveforms, we can obtain single sideband suppressed carrier AM. So the single sideband suppressed carrier can be obtained as follows. In order to suppress one of the sideband, the input signal fed to the modulator is 90-degree phase shift, with that of the signal fed to the modulator 2. So let E1 of t is equal to EM cos omega m EC cos omega CT. E2 of t is equal to EM sin omega mt EC sin omega CT. Therefore, at the summer we need to add these two signals, E1 of t and E2 of t. So the combination of these two signals will produce ET of t, single sideband suppressed carrier waveform, EM EC cos omega c minus omega m of t. We know that double sideband suppressed carrier AM equation is cos omega c plus omega mt plus cos omega c minus omega mt. Whereas in SSB only one sideband is allowed. We can interchange this phase shift in the upper half and the lower half. We can able to select lower half sideband also. It is up to the user constraint. We can select either LSB or USB for our future use. Frequency spectrum of SSB SEAM. So carrier is suppressed, any one of the sideband can be suppressed. So in this block diagram we have suppressed lower sideband, so only we are going to transmit upper sideband alone. So this is a phasor representation. There is no carrier, but it acts as a reference phase. This is the resultant vector. One of the sideband can be suppressed. Here we have taken only LSB. Power calculation. The power in sidebands in SSB is represented as PT double dash, whereas in double sideband full carrier it is represented as PT, suppressed carrier it is represented as PT dash. For differentiating those two terms, here we represent it as PT double dash. So this is equivalent to either the lower sideband or upper sideband. In this case we have considered USB, so P USB is equivalent to MA square VC square by 8R. In terms of carrier power we can write this as MA square PC by 4. The power saving with respect to AM with suppressed carrier is equivalent to PT minus PT double dash divided by PT into 100. So this is total power transmitted of AM waveform. We know that it is 1 plus MA square by 2 into PC. Similarly, the carrier power and sideband powers of SSB is substituted here. While we simplify this, we will get 4 plus MA square by 4 plus 2 MA square into 100. By taking critical modulation as our constraint, 10% modulation, Vm by Vc is equal to 1. So this is equivalent to 83.3%. So the efficiency is drastically improved when compared with double sideband with full carrier and double sideband with suppressed carrier. So that is why we prefer SSB for sending the AM modulated waveform. Thank you.